So good afternoon, everyone, and welcome to this afternoon's ARCHER2 webinar. I'm very pleased to introduce my colleague, Luca, and he's going to be talking to us today about understanding parallel I/O through profiling. So without further ado, please go ahead, Luca.
Thanks, Claire. So thanks everyone for coming. And today we're going to see how we can use profilers to understand the behavior of input-output in your application. So I/O is quite a complicated, deep software stack. Whatever library you're using, it's probably calling various layers of software underneath. And we'll look at how to use a specific tool called Darshan to profile input-outputs at all these different layers. And we'll use two different examples. One is we'll just be writing a 2D array to disk. We'll be doing it in various ways. First, we start by just having each process writing a different file. Then we'll try to see doing actual parallel output by having all files writing to a single shared file. And then we'll see how we can use MPI-IO to make that process easier. And then we will switch to actual concrete example from a real application from fluid dynamics. So the I/O software stack has multiple layers. So the highest level is your application. So you have some data and you want to write them to disk, and you want to do it in a parallel way. So in order to do it in a parallel way, typically you will call some high-level library. So a very common one is HDF5. There are others. NetCDF is a very common one, and typically that will be built on top of HDF5. So HDF5 will allow you to save your big arrays to disk, but it also allows you to save also some metadata, such as information about what that array is about, the sizes, and things like that. And under the hood, HDF5 is calling MPI, and in particular is calling a subsection of the MPI library called MPI-IO, which allows multiple processes to write together to a single file shared by all processes. MPI-IO will handle all the required communication, and in the end will offload the actual task of writing to a disk. And it does that by calling an interface called POSIX. That's a low-level C library that essentially just taps into system calls that allows MPI to write to disk. When you sometimes if you do a sample write from like C or from a C library, you're probably using the standard library, and there's a different interface from POSIX called std.io. And once you call these subroutines, then what the control goes over to the OS, so to the operative system, and usually the operative system will transfer it to the whatever file system you're using. So on ARCHER2 and other big cluster, the file system needs to be accessible from everywhere, from all the login nodes and compute nodes. So typically it will be a network file system, which adds some complexity. So in order to understand what's going on at all these different layers, we need some tool to do that. And Darshan is a tool, a profiler that is able to intercept all these I/O calls from MPI-IO, POSIX, STD-IO, and gives you some information about what is actually going on. It can also give you some information about the file system, and more recent version also support intercepting HDF5 calls. Up to the version we have on ARCHER2 does not at the moment. So we will not be using that feature in this talk. So the first task we're going to try today is to write a 2D array split between different ranks to a file. So logically, the array is a 2D array. So it's split in 4 different subgrades, and each subgrade is given to a different rank. And of course, in memory, everything is really one-dimensional. So we want to store the 2D array in, say, the Fortran way, which means we store everything by column. So we want to first store the first column. So rank 0 will store in some buffer its first column, so element 0, 0, and 1, 0. And then second column, so 0, 1, and 1, 1. And all the other ranks do a similar stuff for their own subarrays. So we want to write this 2D array to a file. So the first thing we'll try to do is the easiest thing, which has each process write to a separate file. So each rank has its own subgrid in column by ordering, and each rank will write to a different file. So that's easy to do. It's actually also efficient, but from a data management point of view, it's a nightmare because you'll get one different file for each rank. You have 4 ranks, that's manageable. You start to have thousands of ranks for just one output of your simulation. That quickly becomes unmanageable, but it's easy to do, and it's a good thing to start with and try to play with Darshan. So we can run this application, can look at how well it performs. So we're running on 4 nodes, and we're using, say, just a few ranks per node. So in this case, 10 ranks per node. And we get quite a good performance of 16 gigabytes per second. But let's look a bit deeper into what happens and use Darshan to do it. So Darshan is already installed on ARCHER2, and it's not difficult to install, but we will not go through the installation process. So on ARCHER2, all you really need to do is to load the appropriate module. So you just load the Darshan module. Then all you need to do is to run your application with srun as usual. So behind the scene, what's happening is that the application will be linked with the Darshan library, and Darshan will, in the background, intercept all I/O calls and save all the tracing information to a file, to a profile file. So once your application starts to run, you might look into your folder looking for this profile file, and you will not find it. So this is because, unlike other profilers, by default Darshan will typically save all the profiles to one single shared directory. You can figure out which one that is by using the Darshan config tool with the appropriate flag. So I'm using my own install, so you can see where all my profiles will get saved. So the directory is structured by the time the simulation was launched. So that means if I launch it on the 21st of January, then 2024, then I will have to look for a subfolder called 2024, 1 for the number of the month, and then 23 for the number of the day in the month. And then you'll find a file called a .darshan file, and that's a binary profile, which is executed by the application. Now you want to be able to, this is just a binary file, so you can just easily see it. So you need to generate some kind of report, which can be read by human. So you can, the quickest thing to do is to generate a visual PDF report, which you can do with a Darshan job summary script. You can also generate one report per file, which can be quite useful. But if your application is doing a lot, creating a lot of files, for instance, doing one file per rank, then you might want to be cautious, or you might get submerged by a lot of files. So once you have generated this report, you can open it. So I've generated a report for this file per process application. So the header of at the start of the report, you can find some general information about the job, like the job ID, how many processes were reached, and for how long it ran. You can see also some overall performance, which in this case between 15 and 16 gigabytes overall per second. Overall your application. So that includes all writes and all reads to all files. You can also see here how much time was spent in doing I/O versus doing everything else, so computation. So in this case, we're just generating some dummy data and writing it to file using the POSIX interface, so quite low-level interface. So you can see that there's quite a lot of POSIX writes going on. There's I saw a little bit, but very little of a standard library. So that's just the application essentially reading and from input file and writing some information on the screen on a log file about what's actually doing. You can also see how many operations are being done. So you can say how many open operations. So many times are you opening a file, how many times are you writing to a file, and for each channel. So in this case, we're using both the POSIX interface, so the low-level interface, and stdio, so just plain C standard library. You can also see the distribution and sizes, which can be quite useful to understand what kind of I/O pattern you're doing. So in this case, you see there are quite a few small reads, so they're just reading a configuration file. And then you have quite a few writes, but they're quite big. They seem to be quite big. And in this table, you can see what are the most common access pattern. So you can see the most common one is a POSIX access. There are like 280 accesses, and each one is an access like a very big, so like a write, and it's over 2 gigabytes. So there are 280 of them, and we have 40 processors, so that works out about, should be 7 write operation for each rank. Plus, you can see there's 40 operations on a slightly smaller one, so that means 1 write per rank. So in total, 8 writes per each processor. We can also see how big the file is. So the file we're generating is about 15 gigabytes, so that's probably what we're writing. So all this information gives you a very quick and high-level view of what's happening, and pretty visual, so it's easy to see. And you can also see a timeline of all the write and read operations per rank. So so the x-axis is time, and the y-axis the rank. Each time you get a line, it means that the rank is doing some read or write operation. So in this case, you can see that rank 0 is doing something for a while, and then all processes start in parallel start to write. So each one will be writing to a different file, and you can see that each one is taking roughly the same amount of time. They're all writing the same amount of data, so that's not surprising. Of course, there's some fluctuation, there's some variation, but overall, they're all taking the same amount of time as you expect. Now, if you want to more information, more specific, you'll need to generate a text report. So you can do that by using the Darshan parser command and apply it to your .darshan file you got from profiling. So by default, if a file is accessed by more than one rank, it will just aggregate all the information over all the ranks. So for instance, if you look at how much data was written, it will tell you how much data was written by your whole application by summing of all ranks. That might not be what you want. So you can disable it by setting an environment variable before you launch the job you want to profile. So if you look at the summary, it will look like this. So you will get this table. So first column will tell you which line is actually doing the call. So in this case, it's POSIX, so quite low level. It will tell you which rank is doing calling the library. Then you have some identifier that just tells Darshan what file are you writing to, and then you get you also get a counter. So the counter is just so it's the statistics that Darshan is measuring. In this case, POSIX opens just means how many times are you opening a file, which in this case is 1. And then that's followed by the name of the file, the file system. In this case, it's work4 and ARCHER2, and the type of file system, which is Lustre. And from here, you can, so there's plenty of rows in the file. So interestingly, you can see the number of POSIX threads, which is equal to 0. So we're not doing any read operation on this file. And the number of POSIX writes, which is equal to 8, which is what we figure out from the PDF report. So things match out, which is good. Other information you can get, you can also get, as you saw before, it was possible to see in the output a timeline. So you can get explicit detailed timeline of all read and write operation, but you need to enable it before you launch the job by setting the DXT enable IO trace environment variable. So you set it, then you launch the application, get a .darshan file, then you generate a special trace report by calling Darshan DXT parser. And you get a text report which can be read by human. And it looks like this. So the first, so the commented section at the beginning, they tell you which file that section is about. So that section will tell you about this data2.out file. It tells you that the information pertains to rank number 2, which run on a certain node. It will tell you a summary of the write and read operation. So in this case, it's 8 write operation and no reads. Again, things match. The file system and the file system type. It then tells you some information about the file system. We know this for now, but we'll get back to it. And then you get a table again with time information. So, for instance, the first row will tell you that there is a call, written, a POSIX call, so from the POSIX layer, emitted by rank number 2, tells you that it's doing a write operation, and it's writing segment number 0, so the first segment, at offset 0. So the offset tells you where in the file you're writing. So in this case, you're just writing on the beginning of the file. It then tells you how big your write or read operation is. So in this case, around 2 GB, so pretty big. And then it tells you at what time that write operation starts and when it ends, or what type the write operation ends. It then tells you what the OST is. We'll get back to this, but for the moment, just think of this telling you which disk you're writing to. And you can see that all these calls on this specific file are writing to the same disk, so disk number 5. So now we've told about our manageable writing to so many file things. So let's try to write to a single shared file. So this will work. So we have your application, and each rank will be writing its own data, but this time to a single file. And each rank will write to a different section. This is still not ideal because the way the data is distributed on the file will depend on how many ranks you have, which is cumbersome if you want, say, to use your output for an input for a different simulation with a different number of nodes, for instance. But still better than having a lot of files. Not that this will work if you use the POSIX interface, but if you just do a naive write to non-overlapping sections of the file using the system library, this will not work. This will result in garbage in the file, and that's because the C library is doing some internal buffering. They kind of assume that each process is the only one writing to the file. So if you have multiple processes writing to the same file, you might get garbage out of it. However, if using POSIX and the Lustre file system, then the Lustre file system will keep care to do everything correctly. So we can run it, see the performance. We're still using 4 nodes and 10 ranks per node, so same amount of resources. But this time, you can see that the performance is much lower. We dropped from 16 GB per second to 3 GB per second. So let's look at why that's happening. So the issue is that we're running a computation on a node, but then we want the output to be accessible from everywhere. That means we can't just save the data directly on the node. It needs to be saved somewhere else. So you have a special server which hosts the disk, the physical disk where the data is, and that's called an OST. So object source target, and that's what we saw earlier in the Darshan trace. And the data somehow need to be sent from a node to OST, and that's taken care of by the Lustre file system. So when we're writing lots of files, each file will be created on a different OST, and Lustre will take care of making sure that all the usage of the OSTs is balanced across your application and across all users on the system. But it takes time to send data. So on one node, I found that usually I can't write more than about 10 GB per second from a single node. And a single process can't really write out more than about 1 GB per second. And interestingly, each OST has a limited speed at which it can write to the disk, because writing to the disk is generally slow. So I found that I can't write more than about 3 gigabytes per second to a single OST. Now, when we were writing just one file per process, we were using all the OST, so that means in principle we can go up to about 50 gigabytes per second. Now, if you're using all that performance, it means no one else can use the file system, so you probably don't want to do that. However, so if you use only one OST, you get about 3 gigabytes per second, which is roughly the same we got with the output of a single shell file. That's because when you create a single file, all of it will just be on IST, so you can't really get faster than those 3 gigabytes per second. So how can you make it faster? So the answer is called striping. So essentially what you're doing is you stripe the file across different OSTs. So each stripe is assigned to a different OST. So in this case, this example case, we're using just 3 stripes, which means we'll be using 3 different OSTs. Then we divide the file in chunks of fixed size, and each chunk is assigned to a stripe. So the first chunk will be assigned to the first stripe, to OST number 1, then the second chunk to OST number 2, the following chunk to OST number 3, and then we run out of stripes, so we start from the beginning, and we assign the next chunk to OST number 1 again, and so on. So we assign all chunks in a round-robin way. So by default, so this stripe size is static, it's not dynamic, so it's fixed, and by default will be 1 megabyte on ARCHER2. So you can change the striping, and that's Lustre command, so it's something coming from the file system. So one of the lower levels of the stack. So you can set whatever number of stripes you want. If you just want to use all the stripes available, you can just set the number of stripes to be -1. So we can do that. We can stripe the file and run exactly the same job, no need of rewriting or recompiling. And we can look at the tracing, see if it worked, and indeed, so we saw the same tracing as before. But interestingly, now you can see that the OST column is writing not just to one OST, but to, well, lots of them, basically all of them, all 12. It's not necessarily the most efficient way, but you can see now we can, in principle, use more bandwidth, so we should be faster. So let's look at the bandwidth with typing, and we get about 4 gigabytes per second. Well, that's better than 3. Okay, so we are using more than 1 OSTs. But for just 4 nodes, it's still way below 16 gigabytes per second. So what is causing the issue? Well, we can look at the timeline from the PDF report and see if we can get some clue there. So remember then, for file per process, all the ranks were taking the same amount of time to write to the file. But now, where we're writing to a single file, still writing the same amount of data per rank, and exactly the same data, but now they're all taking different amounts of time. So the problem is that for performance reasons, the file system BOS will use caching. It means when you write, instead of writing directly to a disk, you write to RAM, so to a RAM memory, so in a cache. And once you finish writing there, which is much faster than writing to disk, then you just keep going on. And at some point, the file system is responsible for transferring the data from the cache to the file system. The problem is when you have several processors, then all these processors might be on different nodes, and different nodes don't share memory, which means they don't see the same cache. So it means there is some synchronization and communication needed to make the cache work and be coherent. The other issue is because you don't really know when the writes are actually done to the file system, you need to make sure that there is no overlapping between the different processors. So Lustre takes care of that by using locking. So essentially it will lock, when a process starts writing, it will create a lock on a section of the file and then blocks every other processor to writing to that section. However, because of the writing can happen in can happen in a delayed, so it can be happen in future time, but you still want to make sure everything is correct when you have several processes writing. It means that often you don't just lock your section of the file, but you have to lock the whole file. And that means that neighboring processes will have to wait for your process to finish before doing the output, even if they're writing to a different section of the file. And that slows everything down. That means output to a single shell file will always be slower than writing to multiple files. Now, what we really want to do is writing these 2D arrays to one to the file in the right order. So we don't want the order to depend on how many ranks we have. So we just want to write the whole column to the file. But the column is spread across different ranks, in this case 2. That means the rank 0 would have to write 2 elements, then jump, write out the 2 elements. So these jumps are complicated to write and also not something Lustre is very good at doing. It's much better doing sequential, continuous reads of large chunks of file, not many small operations scattered through the file. So to simplify, we can improve performance, we can use MPI, in particular MPI-IO. So this allows you to write the data to a single shell file, and it allows you to write to allows processor to write to non-contiguous section of the file, and it has 2 modes: an independent operation and a collective one. So let's run it. Let's check the independent one. Look at performance, and it's abysmal. It's really, really slow. So let's check and see why. So we can look at the tracing data. So here I'm plotting in function of time what each rank is doing. So the white strip means that all the ranks are spending time doing MPI-IO writes. So they're all writings. And then what the MPI-IO will call the POSIX layer. So you can see that there are not one, but several POSIX writes, which are the light blue bands. That's where the process is doing writes. But you can see that the process, there's also these green bands. So that's POSIX reads. So not only MPI-IO is doing writes, it's actually also doing reads, which is surprising because you're only writing to the file. So this is due to an optimization called data sieving. We won't go too much into that, but essentially what it's doing is that MPI-IO is just collecting all these small operations and putting them together in just one big block and then write it to the file. But it has to be careful not to overwrite things. So what it does is first it does a read of what's already in the file, update it with a bits it wants to read, and then write it back to the single shell file. So let's try with collecting and see if we get better. Indeed, we get something more reasonable at 2 gigabytes per second. So let's have a look and see what's actually doing. So now you can see that in the MPI-IO collective operation, so in function of time, most of the ranks are not doing any POSIX read or write. They're doing MPI-IO operation, but they're not actually doing any writing to the disk, except for 3, which are doing writes. Turns out there are actually 3 processes for each node that are actually doing POSIX writes. So we can zoom in, and you can see there's still several small writes interleaved with some bigger chunks. So this is because MPI-IO is deciding that while all the ranks have data to write, only a few of them are actually doing writes. That means the data need to be sent to these special ranks, which we call aggregator, which means there must be communication going. So we can see how much time per rank is spent during MPI-IO POSIX operation. So we can see only 3 per node is actually doing any writing to the disk. And overall, about 30% of the time is spent actually doing writing to the disk. And remaining 70% is something else, likely communication. So we can look at the trace from Darshan. And if we look at the trace, you can see a lot of POSIX calls. So from the aggregators, for instance, rank 0, you can see a lot of calls. Each one will be writing 1 megabyte of data, which is equal to the size of the stripe, and they're all writing to the same OST. Different ranks, for instance, rank 0, rank 256, they're all having the same pattern, but they're writing to different OSTs. The file is striped, so we do expect writes to be done to different OSTs. So what's actually doing is that each aggregator is picking one stripe, and they're just writing to that stripe in chunks of, well, one stripe size, so 1 megabyte. And we have 12 stripes on ARCHER2. We're running on 4 nodes, so that means 3 aggregators per node, which is exactly what we saw in the plot earlier. So this is called a two-phase kind of output. So what happens is you have all your data scattered throughout the ranks, and then there's some collective MPI communication that redistribute the data in continuous chunk on the aggregators. So each aggregators have a continuous chunk of the size of the stripe size, and then just write it to its own OSTs. And then once it's written the continuous chunk, it starts to collect data again. So you go back to phase 1. So you cycle through phase 1 and 2 all the time until you've written everything to a file. So essentially, you're using MPI communication to save time when actually writing to the disk, which is often the slowest bit. So let's now have a look at a real application. And we're going to look at Nektar++. So what we're doing, I actually know very little about this kind of application. What I do know is that it's writing to an unstructured mesh. And I know I'm doing some simple partial differential equation. And I'm going to do a very short simulation just for demonstration purposes. When you do real profiling, you usually want to make sure that your test case is long enough, otherwise it might not be that meaningful. Okay, but that just for demonstration purposes, we'll be doing this on a very short simulation. And we're just running it with a default, so that means unstriped file. So we can look at the access pattern, and you can see that there are a lot of small read operations and a few bigger write operations. So lots of small reads and a few big writing likely happening at the MPI-IO level. So we can look at the Darshan output and see which files are occupying more time. And unsurprisingly, these seems to be checkpoint files. So files that the application saves containing all the information about the field at that instant in the simulation. So most of it is due to write operations, which is what you would expect. But you can see there's also quite a few read operations, which take quite a significant amount of time because probably because the size of the output is so small, and a very tiny bit of metadata operation, which means just opening, closing file, and checking file exists. So we might want to understand more where these reads are coming from. So we can look deeper into the trace and the summary. And we can see that the MPI-IO is doing 2 collective writes. And indeed, we see that there are 2 big writes at the beginning. So that's probably what you want to be a collective write. And then it's doing 1 small write. And so that write is a small independent writes. So that means it's not doing collectively with a 2-phase approach. Instead, all the ranks are writing it. And you also see there are, following the small write operation, there are several read operations. They're all very quick, very small read operations, but quite a few of them. So we like to understand where they're coming from, what they are. And you can see from the summary that there are 14 independent reads, so that's likely what they are. One problem with Darshan will tell you which calls are being done, but not from where in the program, so which subroutine is actually calling them. That's because all it's doing is intercepting library calls. It has no idea where they're coming from. So we can use a general profiler, so not specific to I/O, such as Scalaska, but you can use whatever whatever profiler you fancy. And if you look into it, you'll see that there are several calls to HDF5 which are violated in orange. So HDF5 is a higher level library, and this allows you not only to save your whole data, but also some metadata information, so small amount of information. And what's happening is under the hood, the HDF5 calls are actually calling MPI-IO. And you can clearly see it in the Scalaska profile, where, for instance, when you open the dataset, that will issue some read calls. So that's where those read calls are coming from. They're coming from HDF5 setting things up. So opening the big dataset or reading some attributes from the file. Interestingly, Scalaska also is useful for I/O only in the sense it will tell you how much data each subroutine is calling. You can get them from Darshan, but it won't tell you which subroutine is actually doing the writes. However, Scalaska will not tell you which file is waiting on and will not give you all the details that you can get from Darshan. But taken together, you can get quite a lot of insight. So in summary, we had a overall look at how to use Darshan to profile your application, understanding throughout the stack. So from the MPI-IO layer, the POSIX layer, the C standard library layer, and how you can integrate it with general profiling tool to get a really good overview of what's going on. And it can guide optimizing how you run your application. For instance, you might want to change the typing, or you might want to change the number of aggregators. So by default, it will be 1 per type, but you can set environment variables to tell MPI-IO to use more aggregators. That might be beneficial, might be not. And you can check with Darshan. And that's useful no matter which library you're using, because it's whatever high-level library is calling, under the hood is likely calling some lower-level libraries like POSIX or MPI-IO, and that can be investigated using Darshan. And if you're actually developing an application, it can also understand what the bottlenecks are in your application, and that means how you improve the speed of I/O in general. So thank you. So if you have questions, this is a good time.
So I think Harvey had a question in the chat. He's asking, does Darshan ignore files that are in memory and not the file system?
So it does. I have never been able to see any of the in-system files. So because it's Linux, of course, Linux, everything is a file. And some of those files are actually mounted on a memory. So Darshan usually ignores those, and you often want to, because they often happen under the hood. There is another tool which I'm not covered today, called Recorder, and there you I would say it's not as convenient to use for the way it displays the information, but it will give you more information, including opening these files which are in RAM memory. So for instance, you will see, so if you look at the trace and you look at what happens between the different POSIX writes, you'll see that there are some call to POSIX queues, which likely means, so that's, it's actually a means of communication, but it presents itself as a file mounted on RAM memory. And with Recorder, you can actually see those open and start operations, but you can't on Darshan. So Darshan knows them, yes.
Hi, I have a question or two. Can you hear me?
Yes.
Okay, thank you very much for your presentation. With regards to using different number of OSTs in order to read or write data, how we can actually decide which is a good amount to use?
You mean how many OSTs to use? Well, the either thing is just to run different simulation with different OSTs and look at the output from the profiler, and you'll see what are the speed. So I would say if you have a big file, you're generally better off by using all the types. So generally bandwidth increases linearly with the number of steps, so the more steps you use, the better. However, if you, this is usually true if the amount of data you're writing is very big. So it's very small, that's an overhead from having to contact all these different OSTs, and that also poses more stress on the file system. So it might actually not, so for small write or reads might not be beneficial to typing, but if you're writing a big chunk of data, then it usually is. So using all the steps is often good, but the easier thing is just to measure it.
Okay, thank you for that. And for the scenario where we have cache coherency and file locking in order to ensure that when writing, for example, in a shared file, one process don't write on top of each other. In the opposite scenario where we have, let's say, multiple processes reading from a shared file, how can we prevent a type of racing condition where there is, let's say, one process that has read its entire chunk, but the other ones hasn't read it, and the one that has read it can start, let's say, moving to another part, for example, of the code?
So usually the locking will be exclusive for the writes. You can usually have several processors reading from the same file. So that's usually not a problem because you're not actually modifying the file, you're just reading. Might affect performance, this yes, especially if you have a lot of processes reading from the same file, but that's usually not an issue. So having multiple files writing to the same location is a problem. It's usually a programming error. but if reading from the same location is fine. It's actually what's happening when, say, you're running a job from the central installed, then you'll have several users who are all loading the same application, so the same manner, so they're all essentially reading from the same file, which can be a problem sometimes if you have a lot of users all reading from the same file from many ranks at the same time, especially when you're using, say, Python, which typically when you import a package is just doing thousands of start operations, but that's fine. So performance might be affected, but it's correct. There's usually no rest condition there.
Okay, thank you very much.
I'm Harvey Richardson from the ARCHER2 COE. So for the first point about striping the files, the other scenario that's useful to realize is that if you have either small files or you have a large number of them, then you shouldn't stripe the file at all, which is the default. Right? You shouldn't even try because you have parallelism naturally because you have a large number of files. If you have a few very large files, then experiment with the striping, and if you have something in between, set the striping to something intermediate, like 4 or something. And to the second question, if you were trying to write to and managing the reads to the same shared file from multiple processes, and even worse, multiple processes on more than one node, and you weren't using something like MPI-IO, I think you should try to talk to us, put in a query or something, and we'll look at what you're trying to do and maybe suggest an appropriate way to do it. Because that is a recipe for terrible performance if you get that wrong. So it's a hard thing to manage.
Oh, I'm not suggesting that that should be done. I wanted just for session purposes to I like to have a case where I'm writing parallel to a single file and comparing it to MPI-IO. So
no, I'm responding to the question, not you. The question was asking in a scenario where you've got writes and reads to the same file. Yes. How does Lustre manage that? So it does have locking, right? But that potentially could be extremely depending what you're trying to do. So if you were actually trying to do that yourself, then it's something we would want to give some advice on.
Oh yeah, I understand. Yeah, I've never tried to have both read and write the same time. As you say, I would expect it to be way more tricky to do for Lustre file system.
That's one advantage of using the MPI-IO collective I/O because it's managing that for you. Although you might have to tune that. There are various tunables that you can set that improve that performance that aren't obvious, to be honest.
Yes, I didn't cover that. So for instance, you can change the number of aggregators. You can Kai has a special mode which is it can guess what the access is, and that instead of locking the whole file, it will lock smaller section of the file. So that means you can have a speed increase by using different aggregators per type. So the reason usually the default is one aggregator per type is that you don't really have locking issues when you write into a single type because it's essentially a different file on a different file system. So that can be quite efficient. So Kai does have a way to have, they call it like lock ahead, and you can set it up in MPI. And there's also you can on MPI on ARCHER2 you can also switch between different transport layers, so ECX or SI, and ECX tends to perform better with collective operation, which means for large sizes usually ECX performs better than SI, but there's different trade-offs in terms of memory usage and others. So so the whole point of the profiling is that you can see what the effects of those tunable and settings are. And then you can actually change them and see what's happening. So it's more of a way to guide how you set up your environment and your development.
Thanks, Luca. Any other questions from anybody? Okay, well, I'd like to extend my thanks to Luca for that really interesting talk. Thanks to everyone who attended today, and thank you very much.